Okay, so I'm going to give a little presentation on coal and biomass research and development, and this is going to mainly focus on a meeting that we had in Morgantown last week on this area. The main purpose of the meeting was because we had been working on a number of projects that were where coal and biomass had been kind of intermingling and looking at project development and new products out of the two, and that's kind of where this meeting originated. We were tasked with the Department of Energy through our state energy office to host a meeting on biomass, and I decided to kind of broaden it a little bit and look at opportunities for coal and biomass in the area. So the objectives of the meeting were to discuss the current research that is being conducted in the region on coal and biomass, to provide a networking opportunity, probably the most significant portion of this meeting for those that are working in coal and biomass area, to develop these relationships that are needed to move forward, and also once these relationships are formed, to have partnerships. So as new funding comes available, it's important to have these relationships already built and to be able to kind of hit the ground running, so to speak, as they develop. We had a number of invited speakers to the event that it ranged from folks with local government or state energy office to academics from West Virginia University and also from the University of Kentucky, as well as Department of Energy, National Energy Technology Lab, and local developers, or not local, but developers that are interested in looking at coal and biomass projects. So what I'm going to kind of do is go through, there was a number of about 7 different presentations, and I went through all these presentations are available on our website, which is ahc.wvu.edu. And they're all available in full form, but I went through each of them and kind of pulled out a snapshot so that an overall theme for the meeting could be seen. So the first presentation here was from Jeff Hareholt, who is our director of the State Energy Program. Kind of one of the big facts about West Virginia that most people don't realize is West Virginia is a large energy producing state, and you can look at energy flow in West Virginia in trillion BTUs. The supply in West Virginia is about 3.7 trillion BTUs. That's coming from mostly coal, natural gas, crude oil, as you can see on the left-hand side of that schematic. That's the supply. If we look at where that goes, exports are that roughly 3.7, and imports are the remaining about 1.3. So West Virginia actually produces three times more energy than it consumes. So it's a net exporter of energy. You can see where most of that is going: raw coal, international coal, electricity, and natural gas. If we look at West Virginia and other coal-producing states, is also Pennsylvania. You can see Wyoming is number 1, West Virginia number 2 in terms of coal production. Pennsylvania right behind there at number 4, behind Kentucky. If we look at West Virginia's actual coal consumption, consumption of West Virginia coal and power plants, you can see by county where West Virginia coal is being burned, and it's throughout the east and Northeast is being consumed. So West Virginia coal finds its way into markets not only all over the United States domestically, but all over the world. If we look at the electricity exporters again, in this slide, the lighter the state, the more exportation of electric that it does. So as you can see, Pennsylvania is actually the number 1 exporter of electricity, followed closely, number 2 is Alabama, and number 3 West Virginia. So these states produce a lot more energy than they consume. If we look on the other side of the side of the coin, California is the number 1 importer of electricity, where we see most of our regulations kind of starting, so environmental regulations. So it's kind of an interesting look at the energy picture when it becomes coal. So recently, the state of West Virginia is going through a kind of a review of its state energy plan and how it will move through the future. The WVU was commissioned to do a study to look at coal industry for the energy plan, and this is basically showing the key findings of this study that was just reported to the Public Energy Commission about 2 weeks ago. We know that coal will continue to be a major contributor to the West Virginia economy. We know that metallurgical coal imports to international markets will be important. That's one of our #1 coal exports. West Virginia should continue efforts in promoting coal to liquids industrial development in the state, and also West Virginia coal industry production utilization will be very dependent on national environmental policy, which we all know. If we look at that same energy plan and look at where biomass fits into the state of West Virginia, according to the energy plan, the goal was that we would come in around 140 million on a BTU basis, so we'd be consuming or have potential to consume around 140 million BTUs. Our actual consumption of wood is less than half of this, coming into our first real test of our energy plan, which is in 2015. So wood is behind where the state would like to see it. The next presentation was by two faculty members at WVU, just to talk about biomass and bioenergy projects at WVU and how coal is an important component of that. If we look at total biomass production in West Virginia, we currently have estimates of over 3.6 million tons are produced per year. This production comes from a number of different avenues. The first that we've been very instrumental in estimating is logging residues, and we know that on average we produce about 1.5 million tons of logging residues in the state. These are tops and limbs that are left over after logging, and it just represents sizes down to approximately 4-inch diameter. So it's not everything, it's just a major wood that's left after logging. We know from a study that the Appalachian Hardwood Center did last year that on log landings we're leaving about half a million tons, or 510,000 tons a year. It equates to about, for every 2.5 tons or 2.8 tons harvested in the woods, about 2.8 tons, or for every acre harvested in the woods, 2.8 tons are left on the landing in the form of unwanted pieces of wood. Mill residues, we approximately produce about 25,000 tons a week. This equates to 1.2 million tons. And surface mine residues, we're continually develop estimates in this area, and we have a total of 31.4 tons per acre produced when a surface mine expands. This represents on a yearly basis around 350,000 tons of wood. So woody biomass in West Virginia, when we're talking about byproduct utilization, represents a significant amount of fiber and energy potential. If we look at WVU here in our core research group that has been looking at bioenergy, there's 3 different task areas that we've focused on. The first being sustainable feedstock development, the second being biofuels and hybrid biofossil product development, and the third being biofuels and bioproduct development analysis, which includes life cycle analysis and commercialization. Those are 3 areas that we've focused on in the last several years. One of the projects that has been going on is looking at the thoughts that combining biomass and coal does a little bit better job in the production of liquids than when alone. And this is the production of bio-oils. You can see the chart on the left. This is from Dr. Singh, who's a part of our research team at WVU, looking at the combination of red maple and coal. If you look at the left, this is oil production. If we just concentrate on the blue, The blue bar, that's oil production with just coal. If we look at the next bar is coal and torrefied red maple, increases production, almost doubles the production of bio-oils by the addition of red maple to the coal. You can see that coal and just red maple alone is about the same production of the torrefied, and if we look at just red maple alone on the far right, it's about the same as coal alone. So kind of an interesting look at biomass and coal. One of the work that's being done in pyrolysis and the production of bio-oils, which we think are going to be increased research funding in this area in the near future. One of the big things this conference spoke about was coal and biomass to liquids. Kind of one of the beyond thermal applications. One of the main areas of research in coal is to produce liquid transportation fuels from biomass. And I bring this one up because it's kind of an interesting. We'll talk about this more on some of the other presentations. If we look at the production of coal and biomass liquids, the feedstock requirements for a plant capacity of about 40,000 barrels per day, and if we fire on a 30% biomass basis, it requires about 2 million dry tons of biomass per year to make a plant capacity about 40,000 barrels per day. So it takes a significant amount of wood, not only coal, but also takes a significant amount of wood to make these kind of plants happen. So we'll remember that for future, about 2 million tons a year of wood feedstock. Some of the other interesting novel use of coal and biomass is through direct carbon fuel cells. Dr. John Zonlo is part of our research team, and he's been looking at developing these direct carbon fuel cells. Typically in the past, a lot of work was gone into coal as the source of carbon. Now they're looking at wood as the source of the carbon. And the main benefit of these sort of production of electricity from these systems is your ability to manage the CO2 stream much more effectively. It's almost pure stream of CO2, and that's kind of why this research is heading the way it is. We know that coal is a large producer of CO2, as can be wood. So this is one way that we can really manage the CO2 emissions by producing a clean stream of CO2 that then can be either sequestered geologically or used as another form of energy development. The next presentation was on potential growth of biomass crops on surface mine sites in West Virginia. This is done by Dr. Jeff Skousen. Some of the work that he's been doing in West Virginia on switchgrass over the years, and it's very interesting take on some established research and some long-term trials of switchgrass and various such site qualities and aspects. If we look at West Virginia, we create large expanses of reclaimed mine. A lot of times this land is reclaimed, and as you can see is pasture or hayland, a lot of fescue-dominated stands. His analysis about the 54,000 acres of land reclaimed in Appalachia since in 2010. So it represents a lot of potential sites for feedstock development. Much of the land is underutilized and unmanaged. This is a very typical site in West Virginia. You can see a lot of fescue in the foreground, and in the background a lot of autumn olive, multiflora rose type of crops that is, like it says, it's not being managed at this point and not being used for anything other than, in this case, this is considered a wildlife habitat planting. A lot of the emphasis of his research is why not reclaim this land for biofuel production, have this integrated into the reclamation strategy, and go into it knowing that afterwards that you're going to be producing crops for fuel. Some of the research has been done on switchgrass yields throughout the U.S., including some in West Virginia. Some of the average yields in tons per acre. You can see here from 6.3 upwards of over 8. The goal for Dr. Skaussen's research would be around 2.5 tons per acre. So the original project that he discussed at this was a two marginal reclaimed mine lands in West Virginia. One on the left, you can see the Hobet 21 site. You can see a lot different soil characteristics after reclamation. Then the one on the right was the Hampshire Hill site, so you can see different fine amounts and the different soil chemistry. But if we look at the yields, if we look at the Hobet 21 site in the third year, it was producing about 0.5 tons per acre. This is with no additional management. This was just basically the switchgrass sowed on the site and allowed to take over itself. But on the Hampshire Hill site, it averaged about 3.4 tons per acre per year. So between them, which was a little bit better site, but still was a reclaimed surface mine site, and you can see that the yields can be achieved through a little bit of management. If we look at that Hampshire Hill, the third year, again, on different varieties, we had actual variety trials. The cave and the rock sample reached 4.1 tons per acre. So it looks like the 2.5 tons per acre per year is doable, especially with additional management of these sites. Another one of the projects that's kind of interesting, and we look at these yields of 2.5 tons an acre, is some miscanthus planting trials on surface mine sites in West Virginia. After 2 years at this Alton site, had over 10 tons per acre yields. The average yields were between 10 and 15 tons per acre. This site was a little bit better than other sites in that it had been reclaimed for 20 years, so there was a little bit of soil material being developed, but still there's a lot of acreage out there that in similar state as this site that could be used for production of miscanthus. If we follow up from Dr. Skaussen's research and look at some of the other sides of this, one of the big things that comes up when we look at coal, thermal applications of coal, and also for wood, is CO2 management and ways to improve the environmental aspects of these plants, especially on the CO2 side. And one of those is we were given a report by Dr. Dick Bajura, who's the director of the National Research Center for Coal and Energy at WVU, and he is part of he's a committee member on the National Coal Council. And they looked at the potential for integration of biomass and coal with carbon capture and enhanced oil recovery. So the whole idea here is that we know that through our power plant thermal applications for electricity, we produce a tremendous amount of CO2. Kind of the idea here is that we can use this CO2 to when we geologically sequester this, we can use it to reach oil that's been basically stranded and not able to be produced at economical levels. So the idea is to use these oil reservoirs to store CO2 while at the same time push out oil that has been stranded. In this EIA projection, you can see that through incremental crude oil production, if we added at any given time, right now the EIA production is 720 million barrels per day of shale from tight oil and 3.6 thousand barrels per day if we look at CO2 and enhanced oil recovery. So if we look at that tight oil production, which a lot of people are looking at right now, I mean, this is current as of right now with the Balkan Share and the Dakotas, that a lot of oil is being produced. The projected peak is only about 1.3 million barrels per day, and that doesn't even provide more than 7% of U.S. demand through 2035. So even though we do have a lot of domestic oil, shale oil coming on, right now the estimates are that it's not going to meet a significant amount of our demand. So one of these areas is to use the CO2 sequestration and enhance oil recovery. Again, the U.S. potential for CO2 enhanced oil recovery is about 4 million barrels per day from that avenue. That would be upwards of 40% of consumption estimates if we look at this one, demand. So the interesting part of this, and I guess not a lot, maybe I didn't think about it as much, is basically how do we actually move that CO2, and a lot of this enhanced oil recovery would be done in the traditional oil fields of the southern U.S., Louisiana, Texas, and into Oklahoma. A lot of that CO2 would have to be piped from major utility areas, which would be Pennsylvania, West Virginia, to these regions to be used in the sequestration projects. So something we don't always think about is how we actually move the CO2 to these areas for the enhanced oil recovery. And surprisingly enough, there's a number of CO2 pipeline injection site infrastructures already being developed. So something else that I was not aware of that's going on at this point. So if we look at the coal and biomass to liquids with enhanced oil production, again, we can look at imports over to 2035 with coal to liquids and enhanced oil recovery. We could meet those same numbers as the inputs. So the National Coal Council is the group that just finished this report and looking at ways to use the CO2 from thermal applications to increase our oil recovery. The next presentation, we wanted to try to have a little bit of a kind of a look at the environmental / legal side of coal and biomass to liquids, and we had a lawyer from the West Virginia University College of Law that is very ingrained in this area, has worked for major utilities for a number of years before he came to WVU, and talked about the energy policies and environmental impacts of coal and biomass. And his big talk was geared towards the renewable portfolio standard policies and how they have spurred development in these areas. And one of the major problems with West Virginia is the fact that we do not have a renewable portfolio standard. We only have a renewable portfolio goal, which is a little bit different, and the goals are not as rigorously enforced, obviously, as a standard. So we do not have a meaningful standard. His argument is it does absolutely nothing to stimulate development of these resources, including biomass. It has no activity with respect to regional emissions trading programs that were active several years ago, or climate action planning. And there's no long-term planning process for utilities that might use the biomass in their biomass resources in the future. So a big problem. If we also look at, we do have a pretty stringent goal in that we were looking at 25% would come from renewable energy sources by 2025. But if we look at that actual definition of renewable energy sources in West Virginia's portfolio, these are kind of alternative energy sources that can be included. That includes coal technology, cold bed methane, natural gas, and coal gasification. So a lot of this stuff, well, whether most don't see those as renewable or typically meeting renewable standards in West Virginia, they meet their renewable portfolio goals. So some work needs to be done in this area. We know that biomass could be a substantial energy source for West Virginia, but the policies, the practices, and incentives are not there currently to stimulate this development. So one area that we need to be working on is on the policy side. We had several speak about business development opportunities, and I'm going to kind of not talk about those too much. I want to go right into the coal to liquid side, and that's kind of where a major theme for this conference was this coal and biomass to liquids. We were just awarded a grant from the Department of Energy to look at the feasibility of coal and biomass to liquids projects in West Virginia, and mainly they were not focus so much on research, but the actual feasibility of pulling a project at this scale together, and the sheer amount of wood that would have to be moved, and or short rotation crops, and the amount of finance that would be needed to build such a facility. There's several different technologies, and I'm not going to get into too much detail here, but we're looking at direct liquefaction and indirect liquefaction. The main process that we're focused on in the U.S. is the indirect liquefaction, which is gasification and Fischer-Tropsch, which works well with the wood as well as the wood and coal. Direct liquefaction has not been really discussed for, I think, since the 80s in the U.S., just because of the economics were never thought to be there for direct liquefaction. But according to the DOE report here, that in China, that direct liquefaction is becoming more common when one of their approaches. If we look at the coal to biomass to liquids emissions, and we look at this chart, basically shows, we'll focus on the line. The red line is the petroleum diesel baseline. So if we look at just producing diesel from petroleum, that's a life cycle CO2 emissions and kilograms of CO2 per million BTUs. So it's around 100. If we look at coal to liquids without carbon capture and storage, you can see one of the big issues with coal to liquids technology is a huge amount of CO2 that it produces. So we're looking at much higher life cycle CO2 emissions. The cost is around $84 a barrel, so it can compete on a cost side if we look at traditional petroleum, but on the CO2 side, it can't compete. If we move to the right here and kind of look at some of these coal and biomass to liquids, coupled with a addition of biomass, if we look at the 15% biomass per volume weight with coal biomass to liquids and carbon capture storage, you're looking at the feedstock for petroleum costs of $95 per barrel, and a life cycle CO2 cost anywhere between 60 and 70 kilograms per million BTU. So the obvious benefits are it lowers the carbon footprint from coal, allows biomass to take the advantage of the economies of scale. A lot of these plants are very large, and we'll talk about this in the next set, and take a lot of investment, and the amount of energy from wood just doesn't make sense when you look at compared to coal. And we also have the ability, which the DOE is very interested in, are these drop-in fuel sites. So from the DOE perspective, at this point, the DOE feels that the CBTL process is not really, there's no real research needed on this end. It's a very known technology at this point, and that future research is not needed until we can get potential projects up and running that either on a demonstration scale or a smaller scale, so that some of the performance and technology, the catalyst technologies can be refined. There's more work, they want more work to be done in that actual feasibility side than the actual basic research side. And here's the big one, the conceptual plant design for a CBTL plant is around $7 billion to produce about 50,000 barrels per day. So if we look at that 50,000 barrels per day, that's roughly almost 3 million tons of wood, which is an enormous scale of a facility. You know, it would be something that would draw wood from, would have to draw wood from a very large radius, and you know, potentially from multiple states. You know, they're looking at these profitable crude oil prices between $83 and $92 a million, with the carbon storage estimated to account for about $4 a barrel, the required selling price. So there's dollars left in these analysis for the cost of carbon sequestration. But again, back to the sheer scale, not only a $7 billion investment, but a large amount of wood having to move to meet this demand. And that's what the next speaker from the Department of Energy was Thomas Tarka. He was talking about the kind of the financial side of this. And again, if we look at these, the selling price of the coal and biomass to liquids, if we look on the far right side is the kind of the coal biomass to liquid scenario. This required selling price, the crude oil equivalent, is anywhere from $108 per barrel to upwards of $114 per barrel, looking at the different scenarios of wood and coal mixtures. The main kind of return from this is that today's cost, the $7 billion investment, doesn't make sense at the rates of crude oil equivalency. So making it these prices, today's prices doesn't make sense. But once we hit prices upwards of $130 per barrel, we're looking at diesel prices less than $4 a gallon, and we can economically compete. If we look at these, there's a great term, near opportunity, for a large-scale project. Again, one of the major obstacles is that investment, the capital costs. And kind of the key takeaway from Tom's talk, if we look at the price sensitivity to return on investment, if we look at the scenarios here, and the bottom two scenarios, the green line and the green line and the purple line are just a coal to liquids facility, and the top line, the blue line and the red line, are a coal and biomass, a 50% blend rate of biomass. The one is subbituminous coal, and there's bituminous coal to liquids. We can see that depending on the rate of return that's inspected on investment, we can come in a lot better on the return on this investment, or the price for the diesel. So instead of these analyses being done at a 20% IRR, if you look on the other end of the spectrum at an 8% IRR, which is really not bad, today's standards, that you could price those coal biomass to liquids at around $110 per barrel on a petroleum equivalency. So again, from the DOE's perspective, producing these fuels from coal and biomass is feasible today. There is a near-term opportunity for large carbon capture and storage project integrated in with a coal biomass to liquid. We need to maybe looking at relaxing the return on investment requirement down to 8 through some kind of a government investment or other kind of strategy to kind of look at making that happen. And we also need to make sure to use the CO2 captured as part of a enhanced oil recovery scheme. So that can also be help the economics of the CBTL. The final presentation was from our research partners that we've collaborated with on several projects at the University of Kentucky on the Center for Applied Energy Research, and mainly on clean coal energy research and development. Their technical focus areas have a very large research group there, and they've worked on everything from coal and biomass gasification through large system analysis and integrations. A very, very active research group in the area of coal and biomass, and like I said, we've partnered with them on several projects now. I'm not going to get into a lot of their work on the coal and biomass to liquids, just because a lot of that you've seen. They were also awarded at the same time we were here last week the project with looking at producing. They have to produce a liter of oil or liquid fuel from biomass and coal. So they are scaling up an actual plant as part of the feasibility project and looking at the production actual economics of being able to produce this liter a day of fuel, which isn't very much, but it's going to really help the figuring out the economics of the the system. One of the interesting thing, which is kind of on the side of biomass, but and they say this is one of the ones, even though they don't focus all their efforts on this, is one that gathers the most kind of interest from outside, is the algae bioreactor. And basically, in this project, they're looking at capturing the CO2 from a power plant via slipstream, capturing the CO2 and production of algae that are used either they consume the CO2 obviously to grow, but they use these to harness that CO2 and also looking at the production of liquids from it. So they've scaled up from where they originally started in the lab, being able to, it's about a 250 milliliter size, and now they're up over multiple units at 5,500 liters in size. Basically using plastic tubing that the CO2 slipstream is funneled through to produce the algae that is then can either be harvested for a fuel source, for an oil source in the future, or in their case, just producing more of their algae CO2 tubes. They actually have a field installation site with Duke Energy in the Rabbit Hash, Kentucky, where they've actually have, I believe, 2 of the 5,500 liter reactors, algae reactors on site, capturing the CO2 stream from the power plant right there. I saw also kind of integrated other folks at the University of Kentucky, which I thought was very interesting, how they brought in the local landscape architecture design and had a student design system at developing kind of a new system to build these tubes, and there was a number of different designs, and I believe this is the one that won, kind of a spiral design of these algal reactors outside the power plant. At this point, I think it would take a site the size, I believe he said, of 1,000 acres to capture the amount of CO2 they would need. But I believe that with further research, that's what they're looking at, is try to reduce this site size. So throughout the meeting, obviously the coal and biomass to liquids is the major focus of the meeting, and kind of not only because of the work that we've been doing in this area and a little bit of the work that was just awarded in this area, but also we see that as one of the most promising areas of biomass integration in our state's energy portfolio, just because we know that coal is still going to be our number one energy product, probably followed very closely with natural gas. But I think wood is going to be an important role in both of those areas. So some of the findings that we found that we needed to do in order to continue this research is we definitely need to develop a better means of working with companies, not only the ones that attended this meeting, which we had several, about 10 different industry partners attend, but we need to have much better kind of network of people that are interested in this area. We definitely need, and one of the second big things, we definitely need a potential demo project so that we can actually produce enough tangible material that to make some of the larger players interested in our work. We also want to make sure to do these demonstration projects in such a way that they can move forward on job creation in not only the wood sector, the wood supply chain, but also, you know, on the coal side, especially on the clean coal technology that we've lost a lot of jobs in West Virginia. One of the big ones, some kind of policies in West Virginia to incentivize biomass, and you know, from the research side, it's not really our job. It's just to do this, but definitely having those goals in mind are important. And kind of at the end there's whether and how we can work with companies to kind of lower this capital requirement, rate of return that they're needed, whether it be from some sort of government investment in these projects to some other type of multiple partner investment that can kind of reduce maybe some of the debt financing, and look at ways that we can maybe live on a little bit smaller IRR, and therefore the coal and biomass and liquids would be a little bit more economical. So those were the basic the findings and what we've gone over at the conference. I would be happy to answer any questions if anybody has any.
All right, thank you, Shawn. That was great to get a summary of the workshop and to understand the fact that coal's not going to go away, but as we transition to alternative renewable energy sources, the importance of combining these two different sources of energy is great, and it's great to see that the technology is working, and obviously the economics is going to have to play a role in this as well. So we'll open it up for questions. You can type your questions there in the chat box, and I see we have one already from Dan. The question is, the high yield of miscanthus on reclaimed mine land is surprising. I always thought that miscanthus needed rich soil to grow well. Can you comment on that?
Yeah, I can't comment a lot on that, Dan, because it's not my area, but I know that there's several other slides, and you can go to Jeff's talk. Another site that they had started has very similar yields as this site at 10 tons per acre. And I know that a project that I was involved in this spring where well, it's actually one of the sites that we planted some of the willow on. There's also some miscanthus there as well. In the first year, it's amazing how well the miscanthus had done on that reclaimed service mine. So I think there seems to be a lot of potential for that, and a lot of people are sort of surprised at this point.
Okay, I just typed a question, if you can understand it.
Right. Yeah, if we look at a lot of these large, I guess your question, should I repeat, what about feedstock percentage and co-firing and acres of woodland needed? Yeah, I mean, it's a tremendous amount of wood fiber needed to feasibly co-fire at a large scale. If we're talking a 15% co-fire of a 300 megawatt plant is a completely different story, though, than from a 15% co-fire of a 50 or 60 megawatt plant. That's kind of where we see the best option. In West Virginia, we have three that are very close to Morgantown, the northern part of the state, that are waste coal burners. So they have a fluidized bed system that they produce the electricity from burning waste coal, and that's where wood fits in very well. Not only is it a cleaner fuel for them to use, but it kind of increases their long-term supply of the waste coal because it cuts down on the amount that they have to burn, obviously. And we think we can very easily supply wood to one of these facilities at say a 10 to 15% co-fire rate.
Okay, before we get to Dan's question, just to follow up, it's easier than typing. So you say easy to get the wood. I mean, at what price and how many tons would be needed for one of these smaller facilities?
Well, one of these, if we were look at, if we were going to look at a 300 megawatt facility, you're talking almost 3 million tons of wood at that size, and so that sheer scale. I worked with a power plant along the Ohio that was looking at that size. And at that sheer scale, that is something that I don't think is potentially doable with our supply chain that we have now. Not that we wouldn't have the wood, but I think it's something that supply chain wise it just would not be able to do. We have very large consumers of wood products in the state that buy low quality round wood. When they were running 24/7, they were consuming about 1 million truckload or 1 million tons a year, which is over 100 truckloads a day, and that took a huge procurement radius. So that size scale is not probably feasible, but Michael, on a smaller size scale, a 60 megawatt plant, which might take 600,000 tons of total, which would be about 60,000 tons of wood at a 10% fire rate. That's very doable. So,
okay. All right, Dan's got another question. You mentioned the break-even cost for coal and biomass to liquid to be 105 to 115 per barrel, did they calculate a comparable biomass to liquid break-even number as well?
I don't think in those reports, if you look, the Department of Energy, NETL, just re-updated those and reaffirmed the numbers in those reports, which are available on their website. I do not believe that they did just a biomass to liquid break-even number. And we can look. I'm almost positive they didn't, because those figures are directly out of their report. So and this was just updated within the last, I think it was the last 6 months. So to answer your question, I don't believe so, no.